target detection using multiple foveas. In real context, the robots must be able to find some target according to the task and react to some adverse event during its operation. But this requires runtime process, and this is a challenging task because to the data acquired. The operate environment of a robot contains a lot of visual information, and not all information can be processed at the same time. Then, the robot needs to select the essential information to perform the task. In this work, we build the visual attention process using the foveation technique. Inspired on biological vision, this keeping some small region of the image at high resolution and reducing the resolution according to the approximation to the periphery. Based on this idea, Gonçalves proposed by multi-resolution with features method that select parts of the image and resize them equally to smaller sizes. This method stands out for reducing the processing time in extracting information but keep fixed fovea in the center of the image. Subsequently, Gomes formalized the multi-resolution with moving fovea method that provides mobility to the fovea. During a task, we have multiple targets in the image and need to keep the visual attention in each of them. In this context, it's necessary to move the fovea between targets. However, these movements are expensive and without guarantees that all targets will be tracked. Trying to solve it, we extend the visual system for support multiple foveas. Foveas is widely used in the literature, but there are few references that use the foveas to estimate the target position. We highlight this research because they use a local field potential with foveas to evaluate object displacement, but they didn't consider the weighting of multi-resolution levels. Thus, target detection in other multi-resolution levels is compromised. So, we propose a new approach to target detection using multiple foveas. Okay, the basic idea is to estimate a probability of target detection in each fovea, taking into account all resolution levels, and combine this information to find the target's position. Okay, but how do we do it? A robot task contains one or multiple targets. A set of features stored in the robot's memory represent these targets. The feature is a portion of the image that contains relevant information and it's encoded in a descriptor. During an operation, the robot matched the descriptors of the targets stored in its memory with those acquired by sensors. Matching descriptors results in false matches, the outliers, or true matches, inliers. So, we combine these values into an inliers rate, represented by equation 1. We use multifoveation to put foveas in the images acquired by sensors. These foveas have n levels. Each one extracts features and has an inliers rate associated. But I don't know if the target is at all levels. For this, we propose a level weighting approach, where the level weights are given by the proportion of transformed pixels, defined by equation 2. And the linear combination of weighted levels and inlier rates provide a fovea detection function. It returns a maximum value when the fovea is in the center of the target, and this value decreases when we increase the distance between the fovea and the target. This linear combination generates a detection surface through successive movements of the fovea by the image. But this procedure has a high computational costs. Thus, instead of moving the fovea by all pixels in the image, we code using space around the x and y axis, but this also requires a lot of processing, and the second possibility is keep fixed fovea at strategic points in the image. Okay, we used the last one possibility, and we subdivided the image into 4, 5, 6, and 9 regions. In each subregion, we put a fovea. Furthermore, we propose two methods that move the fovea using interactive mode. We propose they use this information in methods based on gradient descendant, maximum likelihood estimator, multilateration, trilateration, and weighted barycenter coordinates to estimate the target position. The local gradient is calculated by the difference between the central fovea and the neighboring foveas. The region reduction method reduces the search region according to the direction to the local potential field. The local gradient intersection method indicates an estimative of target's position according to the intersection between two local gradients. These methods make use of three possibilities. The first one uses the 8 positions around the fovea. The second possibility uses the 4 positions up, down, left, and right. And last one, use the 4 diagonals. Okay? The detection surface converges to a multivariate normal distribution, where the mean represents the target position. For this, we can use the maximum likelihood estimator. In these methods, we interpreted the detection of the fovea as a circumference that increases when the detection values decreases. In other words, there is an inversely proportional relationship between radius of the circle and the detection value. These methods estimate the target position using the intersection between the circumferences. And for that, they need information about the distance between the foveas. This method implements an interpolator that uses 3 foveas to estimate the target position. We select 3 foveas according to their proximity and maximum detection values together. We weighted their position using their target detection values. We used the toy video for visual tracker benchmark to validate our theory. This video contains a sequence of 271 frames under scale variation, fast movement, and rotation of tracking target. The target was extracted from the first frame of the video, and we use foveas with 4 levels and surf feature. In our results, we calculate the mean error using the Euclidean distance between the estimated positions and the center position of the ground truth region. These results demonstrate that the mean error of local potential methods are greater than 76 pixels, and there is a scattering of errors generating a high standard deviation. This information indicates that the methods may not converge to target position. These results show that mean error of estimated position by multilateration, trilateration, and barycentric coordinates are most accurate than maximum likelihood estimator. Furthermore, we can observe that the standard deviations of the multilateration errors for the 4 settings show little variation because this approach uses all fixed foveas to estimate the target position. Our conclusions: we propose a new target detection approach, exploring several mathematical strategies in this work. We conclude that the trilateration, multilateration, and barycentric coordinates perform better compared to local gradient and maximum likelihood estimator. We can detect the target position using at least 3 foveas, and in future work, we will study the multiplicity of identical or similar targets, target absence, and real-time application. This is my reference, and thank you.